BH and BC. It's statically determinate, so before we even make a plan of the cut to make, or if we want to use method of joints, we're going to solve the external picture, get those reactions, and then assess what our next move is going to be from there. So first free body diagram is going to be that external picture. So I'm going to free it from its pin at A and its roller at E. But I also have to include all of those external forces on it. So a 30 kilonewton force here, a 20, and then a 40. So the support reactions we have here, this is just like a chapter 5 question at this stage. I'm not doing, nothing is internal in this picture. The roller is going to have an EY, just that normal force. I'll have an AX and I'll have an AY. And in this problem, all of the spans are 4 meters long. So from the external picture, I can find my supports. So in picture number 1, summing forces X is going to be AX. In the Y, I'll have AY plus EY minus 30 minus 20 minus 20 minus 40. And I can take the sum of moments around a point. I have a pin at A in my external picture, so just like we saw in chapter 5, I'll just take the moment about A as well, or because of that pin being there. AY, AX do not appear in the equation. The 30 kilonewton does not appear in the equation. So I have negative 4 times 20 minus 8 times 20 minus 12 times 40 plus 16 EY. So by design, EY is the only unknown in equation 3. So that normal reaction is going to be 45 kilonewtons. Putting that into equation 2, I can get the support at A is 65. All right, so nothing new in this one, just chapter 5, find those supports. But we have to address now what we wanted to find, these 3 internal forces. And in this picture, it can help, especially for more complicated ones. I just want to mark the ones that we're interested in. So this one's pretty straightforward. We want to see, can we make a cut that goes through all of them, or as many as possible, and we'll only go through up to 3 of those members. So we're making a loop that does that. So we can make one cut. It's going to be a vertical cut here. But then we have to decide, do we want our loop to, what do we want the loop to contain and what do we want it to exclude? So usually my rule of thumb for what do you include rather than exclude, I want to include the smallest amount possible in my picture. It's just less to draw, and then there'll be fewer things to include in equations that come out of that picture. Here it doesn't really make much of a difference if I loop to the left or if I loop to the right. I'm going to have 2 applied loads either way. AX happened to be 0, so I'll have one reaction force either way. In some problems, though, it's much more obvious that you can take a much smaller picture rather than the much larger picture. You're going to get the same answer either way, but it's just less work. So just because it's less of the picture, I'm going to take everything to the left as this will make picture number 2, which will be my first section cut. In this case, the only section cut I need. So if this is the middle, then this is slightly less than the middle, but it doesn't really matter in this case. It doesn't save me too much. So in my picture 2, I now draw everything that's intact in my loop as intact, and everything that's cut through, I'll now be able to see the forces in those objects. So A, B, J, and I are unaffected. They're just inside that loop. Nothing's being cut through. So since those joints are intact, then the forces acting on them are also intact. AY is intact, and I found it was 65. And AX I found to be 0, so I'm not even going to draw it in this picture. I could, but it has a value of 0. So now the members that I cut through, I can now see their forces in this picture, but I couldn't in this one. So I have FHI, FBC, and FBH. Again, they chose to use a 1-1 root 2, or a 45-degree angle triangle in this case. So in my second picture, I've introduced 3 unknowns, but I've introduced also a new rigid body free body diagram, so I can get 3 equations out of this. So picture number 2 will give me another set of solvable equations, and the 3 unknowns are also the 3 unknowns that ultimately I needed to find. Again, I'll reiterate, it's not always possible to get away with just one cut that will go through everything you want, but you want to start with a section, and then you can add more sections or then move on to pin diagrams to get the rest. It can still save you time overall compared to going all the way through with analyzing the pins. So using my second free body diagram, I'm actually going to start with summing forces in the y direction. That way I can start to get numbers right away out of this. So the order you do it in doesn't really matter. So in the y direction, I'll have the AY of 65 minus 30 minus 20 plus 1 over root 2 FBH. So by starting with y, I can get FBH right away. So equation 4 gives me FBH, negative 21.2 kilonewtons compression. I can now move on. I'll actually go to sum of moments next in picture 2. So in the internal picture, I can now look at, I would choose point B to take the moment about, because I have 2 of my forces with their lines of action passing through it, so that'll leave me with just FHI as my only unknown in equation number 5. Okay, so at B, I have FBC, FBH. I also have the 20 kilonewton load with its line of action through B, so that none of those 3 will contribute to the moment about B. However, I will have, this is 4 and 4, negative 4 FHI plus 4 times 30 minus 4 times 65. Right, so from AY, the applied load of 30, and then FHI all contribute to the moment. I can cancel out that 4 to make it just a little bit simpler, but equation 5, now I can find FHI since it was my only unknown. So FHI, I get a negative 35 kilonewtons, also in compression. One unknown remaining. It's in my free body diagram, so now I'll write sum of forces in the x. Because the only thing now numerically I don't know will be FBC. So in the x, I have FBC plus FHI, which I just solved for, plus 1 over root 2 FBH, which I have from equation number 4. So putting equation 4, or solution from 4 and solution 5 into 6, my last unknown, FBC, I can solve. So FBC, I get a positive 50 kilonewtons, so that's in tension.